Okay, we return another integral. This one's from JEE Main 2002. We've got the integral from minus pi to pi of 2x times 1 plus sine x over 1 plus cosine squared x dx. Okay, to get started, my first thought on this is just noticing we've got bounds that are symmetric around 0. And like we see cosine squared is an even function, it's making me think that we can use odd and even functions on this. But first what I want to do is split this up, just distributing in this 2x and dividing it into two integrals on this plus sign. So for the first one, we have the same bounds, and then the numerator is just going to become 2x over 1 plus cosine squared x. And then for the second one, when we distribute 2x to sine x, then our numerator is going to be 2x sine x over the same denominator. In doing it this way, what we notice is this first function here, this is an odd function. The reason this is odd, our definition for an odd function is just f of minus x is going to be the same thing as minus f of x. So if you take a minus x and you plug it in here, the minus is just going to come out in the numerator. It's going to get wiped out in the denominator, and so this is going to be true here. We have this principle that we can use for odd functions, that if we have bounds finite, symmetric around 0, and f of x is odd, that tells us the whole integral is just going to be 0. So we're just going to wipe out this first part. This whole thing is going to be 0, and we can move on to the second integral. Now for this one over here to the right, what we notice is this here, this is going to be an even function, and our definition for an even function is that f of minus x is going to be just f of x. You can see how this is going to work. Now like on the denominator again, same as over here, you plug in a minus x, it's not going to matter inside the cosine function. If you plug minus x into the numerator, you have 2 minus x sine minus x. Well, I can write this as minus 2x, and then here sine's an odd function. I can bring it out front like this and write this as minus sine x, but multiplying it out, this is going to be the same thing as 2x sine x, and this is going to be the same thing as our f of x function, so this thing is even. Now the principle of even functions we want to use in this, really similar but not quite as useful. We have symmetric bounds around 0, f of x is going to be even in this case. What it's going to allow me to do is bring a 2 out front, change the lower bound to 0, and just rewrite it like this. So using this property, we can take this and we can rewrite it with the 2 out front. Now we're going from 0 to pi of all the same thing here. But now here, this is about as much simplification I can get with odd and even functions, and now we're going to have to just deal with this integral here. And I think what I want to do for this is use King's principle on this, just noticing our bounds going from 0 to pi. Let me make some more space and we'll continue from there. Okay, making use of the King's principle formula we have down here, what we're doing is we're calling this right here is going to be our f of x in this. And so what we're going to want to do to transform it is we're going to want f of b plus a minus x, where our bounds are just the a and b. So when we write this over here, for our f of b plus a minus x, just adding the bounds together, this is going to be f of pi minus x. So when we do this, our bounds are going to stay the same, still going from 0 to pi. But we need to plug in pi minus x everywhere. So in the numerator, we're going to have 2 pi minus x sine pi minus x. And then here, I didn't really give myself enough space, but I think it's going to work. So for cosine, this is going to become cosine squared pi minus x. Now to simplify this, there isn't too much I can do with this except for distribute it out. But for sine pi minus x and cosine pi minus x, we have the supplementary angle formulas. So for sine pi minus x, that's going to be the same thing as sine of x. And then for cosine pi minus x, this is going to be the same thing as minus cosine x. So when I rewrite this, first I'll take this 2 and bring it outside, so I'll have a 4 now in front of the integral. Then I'll leave this pi minus x for now. And again, sine pi minus x, this is just going to become sine of x. And then in the denominator, I can basically just turn this back to cosine x, because again, the square is going to wipe out the minus sign, so this is going to become 1 plus cosine squared x dx. And then from here, all I want to do is I want to distribute the sine into this here and break this into 2 integrals. So when I do that, let's see how this is going to look. For the first one, it's going to have a pi in it. I'm going to bring the pi out front of the integral. So for this first integral, I'm going to write it as 4 pi. And then this is just going to become sine x over 1 plus cosine squared x. And for the second one, breaking down the minus sign, I'll bring the minus out front. So we'll have minus 4 same bounds, and this is just going to be x sine x over 1 plus cosine squared x. And then at this point here, what we notice is this whole thing right here, including the 4, this is going to be exactly the same as this. It just looks a little different because we have the 2 inside the integral here, but if you pull out the 2 here, you get the 4, and so these are identical. So what I want to do is put some labels on things. If I just label the original integral I, come down here, this is still I, well then this is an identical copy of I. So what we can do, since we're subtracting I here, if I just add a copy of I here and add a copy of I right here, then this is going to cancel out. This is an integral we can do, and on the left side of the integral we have just 2 copies of I. Okay, at this point we're getting close, but let's actually just isolate our goal, which is I. So if I divide off 2 here, I can divide 2 here. 4 divided by 2 is going to turn this into a 2. And now what we have left here isn't too bad. I think we can just do this here with a u substitution. If I set my u equal to cosine of x, then take a derivative. du is going to be just minus sine x dx. While I have the sign, let's just create the minus sign here in order to make this easy. So I'll multiply and minus, so we have our du in the numerator, but I don't want to change it, so I'll multiply by minus in front. Then next we'll go ahead and substitute. First, updating our bounds, if you plug pi in here, the upper bound becomes minus 1. You plug 0 in here, cosine of 0 is just 1. Then transforming the integral, this is all going to become du over 1 plus u squared. I can use this minus sign here and use to swap the bounds, so we can put this back as going from minus, so I can flip it and write it as minus 1 to 1. And one last thing before I integrate, let's just notice that this is an even function. I can use here the principle of even functions, that if we have an even function, bounds symmetric around 0, I can update the lower bound to 0, and then just multiply by 2 out front. 2 times 2 here is going to give me a 4. And then we'll just go ahead and integrate this thing. We'll bring 4 pi in front. Integral here of du over 1 plus u squared. This is just going to become arctan of u, and we just need to evaluate from 0 to 1. Evaluating arctan at 0 is just 0, so we just need to evaluate arctan at 1. Bring the 4 pi in front. Arctan of 1 is going to be just pi over 4. Multiplying this out, 4's cancel. And for my final solution of this, we just get pi squared. Okay, there you have it. Good one from JEE Main 2002. Thanks everyone for watching. Have a good day.